General equilibrium with Kc, Kp, and Le Chat's. First key concept, general chemical equilibrium is reached when two opposite reactions occur at the same time with same rates of reaction. Species concentration become constant but not equal. So Kc is found by doing concentration of products over reactants, and the coefficient of each chemical species becomes its power. Kp is for pressure, and pressure is indicated by using parentheses, and similar to Kc, you would do pressure of products over reactants. Fourth key concept is Le Chatelier's principle. So manipulating a chemical species, adding a reactant causes a shift right, adding a product causes a shift left, removing a reactant causes a shift left, removing a product causes a shift right. With pressure and gas, increasing a pressure, decreasing volume causes the reaction to shift towards less gas molecules. Decreasing a pressure or increasing volume causes the reaction to shift towards more gas molecules. Adding an inert gas has no effect. With temperature, in an endothermic reaction, heat is on the reactant side, so increasing it causes the reaction to shift right towards products, and decreasing it causes a shift left towards reactants. In an exothermic reaction, heat is on the product side, so increasing it causes a shift left towards reactants, and decreasing causes a shift right towards products. Fifth key concept, manipulating K. Reversing a reaction means using the inverse value of K. Multiplying reaction by coefficient means that you should raise K to that power. And then adding reactions means you should multiply the equilibrium constants to get the final K. Sixth key concept, comparing Q to K. Q describes the amount of products to reactants at any point in the reaction, whereas K describes the amount of products to reactants only at equilibrium. So when Q is less than K, a reaction will proceed forward. When Q equals K, reaction is at equilibrium, so concentration of reactants and products remain the same, whereas when Q is greater than K, a reaction will proceed in the reverse direction towards reactants. So this is the first diagram for equilibrium. In the bottom diagram, the reactants and the products cross over, and then at this point they're in the same slope, which indicates that they're at equilibrium, same rate. This is the Haber process where ammonia is produced, and then this graph shows the equilibrium variance. So when hydrogen gas is added, there's a disruption, so that's the peak, and then over time equilibrium is reestablished, and that's noticed by the same slopes. This graph shows catalyst in equilibrium. Green line is with catalyst, and then the purple is without. So catalyst reduces the energy needed and speeds up the reaction, so helping reach equilibrium sooner. This shows magnitude of K increasing, so with more reactant particles and less products means that K value will be small. With relatively equal amounts of reactants and products means K is an intermediate value, and then if the reactant particles are very low, whereas particles are very high, K is a large value. Alright, so here's the free response example for equilibrium. They give us the reaction carbon solid plus carbon dioxide equals carbon monoxide, and then A asks for the Kp expression, so you do pressure in parentheses of only the gas and not the solid. So you do pressure of carbon monoxide squared because of the 2 coefficient over pressure of carbon dioxide. B asks for moles, and you use the gas formula because pressure is given in the table, volume and Kelvin are given. Since it says initially placed right here, you would use the pressure at initial time, so 0 hours, 5 atmospheres, and then 2 liters given. R constant, which is 0.0821 times the Kelvin given, and that equals an N equaling 0.105 moles carbon dioxide gas. C asks for the partial pressure of carbon monoxide given the partial pressure of carbon dioxide. So use partial pressures. So total pressure would be carbon dioxide plus monoxide. So to find carbon monoxide, you'd subtract. And total pressure is found in the table at the end hour, so at 10. So that's 8.37 atmospheres minus 1.63, and that equals 6.74 atmospheres for the partial pressure of carbon monoxide. Second part of C asks for the Kp constant. So you'd use the one that we set up in A, and then you'd plug in numbers we just found for carbon monoxide and then given for carbon dioxide, so 6.74 squared over 1.63, and that results in 27.9. D asks for whether when a catalyst is added, a suitable catalyst is added, if the total pressure of gases at equilibrium will be greater than, less than, or same when compared to equilibrium without the catalyst. The answer is that the total pressure remains the same because the catalyst only speeds up a reaction. It doesn't affect the extent to which a reaction occurs, so it doesn't affect how much gas is produced or reacted, only speeds it up. And E asks or gives us more information, and then it asks us to produce predict the partial pressure of carbon dioxide, saying that it approaches equilibrium. So since it approaches, you use Q, you plug it into the same formula, and you use 2 atmospheres as it's given, and you compare it to K. Since it's smaller, it proceeds forward. So as it proceeds forward, the reactant carbon dioxide is consumed, so the pressure of carbon dioxide decreases as it approaches equilibrium.